Today's class is about color theory. Primaries. Primaries are colors that together you use to create all other colors. And these are true primaries. Why these are true and what non-true primaries are, I will explain in a minute. But first off, RGB. You've heard of RGB. This is what your computer screen uses to make all colors of light, and this is what your Epic gaming keyboard is. With red, green and blue, we can make all colors in an additive context by adding light. So here I am making green light and then I am adding some more blue light over it. Together, these can make other colors, and this is additive because you are literally adding light. I am having some green light, blue light. If I add these together, I will get what's in between them. Cyan. So RGB colors, if they work additively, they can make all other colors. And you can also have colors create other colors subtractively. These subtractive primaries are cyan, magenta and yellow. RGB, red, green, blues, CMY, cyan, magenta and yellow. And this one you might know from printer ink. Together these dyes can make all colors. And you'll see here that these added together, hey, they've just made our good old red, green, blue colors over here in a triangle. And if we look in between the red, green and blue colors, we can see cyan, magenta and yellow. So here in a color wheel we have a triangle from red, green and blue, and their opposites are cyan, magenta and yellow, like this. So we have the additive primaries and their opposites are subtractive primaries. Now, who figured all of this out? That is Isaac Newton. Isaac Newton, he put some light through a glass and it was refracted into the rainbow. In last lesson we talked about refraction shortly, about, for example, the index of refraction. And this is actually slightly different for different wavelengths. So that's how a rainbow can form through white light, because they're all kind of being refracted in a slightly different angle. And then moving on to the classical primaries, you may have heard of red, yellow and blue, RYB. You've probably been taught that in school. So if these are the true primaries, then what are other primaries? Are they wrong? Well, this is how light works, additively or subtractively. But paint mixing, in pigments, it's not quite as simple as dyes. For example, printers use dyes, and these subtract well. So with these dyes, you can make all colors. But there are other primary colors people prefer for painting. Not all paints might work in a precise subtractive way. So paint mixing is more nuanced, personal and opinionated. And I'm not going to tell you which colors you need to use for painting or which ones are wrong. This class is about how light works, and how light works is additive or subtractive with RGB and CMY. And this is why these are called the true primaries. This is how they work in nature, how they work in physics. What is color, actually? This is the visible light spectrum. If you've had physics, you might recognize this. Light particles or waves, they have a different level of energy. And if they have a very low energy, they wave slowly like this. They have a long wavelength, like here. But if light gains energy, it starts vibing faster. Its wavelength decreases. So red light, if the wave has a long wavelength, but then blue light has a lot shorter wavelength. So blue light, it has more energy, and the hottest part of a flame, for example, is blue. Wavelengths, as they change, and this one is the other way around, by the way. This is the red begins on the left here, because that's also the way it starts here on the color wheel I have. So I mirrored it for convenience. The color wheel. How does the light spectrum here, how does that wrap around into the color wheel? Because light, it doesn't stop at red over here. It just goes on into infrared, into light we can see. And blue, it doesn't stop here. It moves on to ultraviolet that we can see. So it continues on this side and on this side. It doesn't stop there. How does it wrap around to the color wheel? Well, let's first look at how we see light. Our eyes, this is our eye, it is sensitive to red, green and blue light. And here, these are some shapes over the frequency spectrum. So we are sensitive to blue, green and red light here. How do we see yellow? We can see yellow. We don't have cone sensitive for that. When we see the yellow wavelength, we recognize this as well. That's pretty close to the red wavelength that we are sensitive to here. And that's pretty close to the green wavelength that we are sensitive to here. When we see wavelength, the yellow wavelength, this simply tickles our green and red cones at the same time. We don't see the actual wavelength yellow. We don't really care. Now a color, it doesn't have to be one specific wavelength. It can be a whole range of wavelengths. So for example, a green color, it doesn't have yellow or cyan. So you can draw a curve like this, with a lot of all colors together, they are white. And no colors, no light, that's black, of course. If I look here into my RGB circle, my primaries, in the middle there's white. When we see green and blue and red light at the same time, we see white. So on a black wall, adding red, green and blue light can make white. And on a white paper, using cyan, magenta and yellow, dye or something else that works subtractively, we can make black. So when we see all wavelengths at the same time, we see white. When we see none, it's black, of course. And when we see some, that can look like this. This we would see as yellow. Now light, when you add red and green light, the red wavelength and the green wavelength, it doesn't become the yellow wavelength, it's just the red wavelength and the green wavelength at the same time. And we recognize both of these at the same time and we see yellow, we see the average kind of what's in between them. We can see the yellow wavelength over here, but we can also see the red wavelength and green wavelength at the same time, and we also see yellow. Our eyes don't care if it's actually this one or this one and this one. That looks the same to us. So yellow, it is an actual wavelength, but we also see it when we see a mix of wavelengths. The same for cyan. You can also see cyan, it is in between green and blue. Now, how does the light spectrum actually wrap around to the color circle? Here we have the rainbow. And just like Isaac Newton this is just it's the same. It's just white light that is being split off into multiple ranges, because there are droplets in the sky, and then to your eye here maybe, they refract at a different angle. This is a different angle. So that's why rain droplets in the air can make the rainbow, because the refraction changes for different wavelengths. But anyway, the rainbow, we have red here, just like we have red here. We have yellow here, just like we have yellow here, and green, and cyan, and blue. And in a color circle, we also have red. We begin here, and then yellow, green, cyan, blue. So just like the rainbow, just like the light spectrum, and this part of the color wheel it ranges from a low wavelength to high wavelength. But our color wheel, it continues. It doesn't stop at red like it does here, and it doesn't stop at blue like it does here. This is the color magenta. And if we look at the rainbow, or the visible light spectrum, where is magenta? We cannot find magenta in the rainbow. Just like we can't find it in the color spectrum. You can see in the circle on the right, it moves along in a circle like this until magenta. It doesn't go there. What's in between red and green is yellow, of course. What's in between cyan, what's in between green and blue, it's cyan, of course. But what's in between red light and blue light, it's everything. So how comes magenta is in between those? Magenta is not actually in the light spectrum. The magenta wavelength does not exist. The visible light spectrum wraps around with us imagining a new color in between. When we see red and green light, we recognize yellow. It's not the actual yellow wavelengths, we just recognize it as such. And when we see green and blue, we recognize the cyan wavelength. We can also see the cyan wavelength by seeing green and blue, but the cyan wavelength also exists. It's also its own wavelength. Magenta we see when we see red and blue together, but it's not actually its own wavelength. So that is how the visible light spectrum wraps around to be the color wheel. And that's fantastic because we can apply all kinds of artistic theory to the color wheel. So moving on. Yes, RGB and wavelength absorption. We see a material because it reflects red light and it reflects green light and it reflects blue light. If we see this, our eye here, we see red, green and blue light at the same time. What do we get? We get white over here. I can also demonstrate this for a moment. Let's try adding red, green and blue light. I need to pick the blend mode normal. It just mixes the light that is on the canvas and the light that I am drawing on it. But if I pick an additive blend mode and I draw red and green and blue, then in the middle I get white here, and of course cyan, magenta and yellow. So if we see red and green and blue light at the same time, we see white light. That is what white light is to us. This is the surface of an object, and it reflects red light and green light and blue light. Of course, it also reflects the yellow and cyan wavelengths, maybe. But we see red, green and blue. So in reality, it's a range of spectrums. It may look like this, it may look like this, or it may look like a whole range of frequencies like this, but we just see it in terms of how much red is there, how much green is there, how much blue is there. So that's why I'm talking in RGB right now, as if light is actually just composed of those three. It's not really, and I'll talk about that in the end. That's a bit advanced. But for now, let's act like light only exists in red, green and blue wavelengths, and the others are actually just a blend of those. We are working in an RGB model right now, where we just talk about three of them and not the whole spectrum, because that's a simplification of reality of how our eyes work. So this object that reflects red, green and blue light, what if it just reflects red light? Well, then of course we see it as red. Then it absorbs green light and it absorbs blue light. If it bounces red light and it bounces green light, but it absorbs blue light, then we see it as we see red light and green light. What did we get when we saw red light and green light? When we see red light and green light, when it absorbs blue light, we see red light and green light. And what's in between? Yellow. Just like here, red light and green light, yellow is in between in this additive blend mode. An object that absorbs blue light, that's yellow, because we see the red light and the green light. Another way to think about it is this yellow object, what does it absorb? Its opposite color, blue. Let's think about it in another way. Let's say this object is cyan. I am seeing cyan light. In order for me to see cyan light, I need to see green. I need to recognize the green and blue light. So this cyan object, in order for it to be cyan, it needs to absorb red light. Because, again, green light and blue light, they form cyan. Let's look at what happens if we do the opposite color, cyan, magenta and yellow. In a subtractive blend mode. So if I subtract red light, I should get cyan. Because this white light, it has red, green and blue components. I removed the red light, so it goes more into this direction. It's now green and blue light because I removed the red light. So now to make this white magenta, I need to subtract green. And then to draw yellow here, I need to subtract blue. Okay, now by subtracting red light, I've made cyan, because that's the opposite. By subtracting green light, I've made magenta, and by subtracting blue light, I've made yellow. And by subtracting all three, I've made black. And in between are red, green and blue. Okay, so I said that in order for this object, that's a very ugly eye, in order for the object to be cyan, it needs to absorb red light and then bounce green light and blue light. Because green light and blue light, if I again switch to an additive context, green light and blue light, they make cyan here. That's how you can think about that. And now let's look at these cubes. Let's focus on these. I'll draw around them in red. We have a blue, red and yellow cube here. So blue, that's blue, if we are talking about RGB. And red is red. And yellow is red and green. That's what these three cubes are. In white light, in red light is bouncing, green light is bouncing, and blue light is bouncing. So let's draw these for a moment. We have this blue cube here, a red cube, and a yellow cube. The blue cube is blue because, of course, it bounces blue. And it absorbs green and red. The red cube is red because, of course, it bounces red light and it absorbs green and blue. This yellow cube in an RGB model, this is a simplified from reality. This yellow cube would then bounce red light and green light at the same time, but absorb blue light. Red and green, what's in the middle? Yellow. So what happens if the light, it's no longer red, green and blue making white, it's now red light that's being that's shining upon it. Now red light, the blue cube here, the blue cube absorbs red light. So if we remove the others, if I just, let's see, I want to show that I've removed the light, but that you still see what used to be there. So I'll do it like this. I'll remove the green and blue components from each of them. Now what has happened? The blue cube does not bounce anything. Because the red light, it's a blue, so it wants to absorb the red light. And what do we see here? It has become black. The blue cube in red light has become black because it wants to bounce blue light, but there is no blue light, there's red light. And it absorbs that. The red cube, of course, it stays red. Because, well, the green and blue light, it absorbed that anyway. And it can bounce this red light that's coming in here. But this yellow cube, it could bounce both red light and green light. So the yellow cube has become red. Because this yellow cube was red and green. This is how colored light works. Why some objects become black in it and why some objects become the colored light. Actually, I'll keep that. And I will come back on this later, because what I've just told you, it's correct here, but it is not necessarily correct in nature. All the way at the end of this lesson, I will call out small imperfections. So, for now, this is how we will assume how objects work with RGB light. Now, we've talked about light in terms of, well, it can be one wavelength, it can be multiple, it can be a whole range. But we don't care, we care about how much red we see in there, how much green we see in there, and how much blue we see in there. Now, what is saturation? Because that has not been explained by this light spectrum or this color wheel. First off, the value is how dark it is. If here I move this up, the value goes from dark to light. Doesn't matter where this is the value. And in your software, this color circle, it might be oriented differently, it might be mirrored, that's all fine. Or it might not even be a circle, it might be a triangle. It will still give you control over the red, green and blue, or the value And saturation we are going to talk about now. What is saturation in terms of wavelength? Here we have a hilariously funny image, and if this is very saturated. If I look at these colors, what do these colors all have in common here? They're all the way to the side. This yellow, it's not a yellow mixed with white, it's all the way to the side. So saturation is just on our color wheel, how much to the side it is. What does that mean in terms of the light spectrum? White light is all of those, of course. So a light that is all the way to the middle, that's very desaturated. And just black, gray and white, that's not saturated at all. How much the color is to the side, that is what the saturation is. But what's happening here actually? Let's pick a yellow color and try to make it less saturated. We have a yellow color here. Now, to make it less saturated, it needs to move more to the middle. Now, what does that mean? Moving on to the middle, it means that there are other colors in here, because white, of course, white was red, green and blue light in our RGB model of reality. So yellow being red and green, to make it more white, it needs to have all colors. Let's do exactly that. Let's go to addition again, and we are just going to add other colors. Let's add some magenta here. Let's just add some red here. Well, there's already a lot of red in it. Actually, I'm going to make already a slightly desaturated yellow. Yeah. Okay, this yellow, let's make it less saturated. I'm going to add some reddish. I'm going to add some green. Well, it should be less actually. I was putting way too much. But we are going to add other colors slowly. Let's add some magenta over here. And some cyan. And some blue. What has happened here is that our yellow, what if we were to move down here? Let's look at this color wheel, what happens. Hey, huge success, it's moving towards white. By adding other colors with an additive blending mode, we have desaturated our yellow. So that's what's happening. To desaturate, you need to add more of the other colors, more white. Oh, that's big, yeah. More white. And to have it fully saturated, we want no other colors in there. We want just this yellow. So talking about a curve, what would be a curve somewhere in between this and this? What could we change to get more? We want to add more green, we want to add more red, we want to add more blue, but mostly we want to just add some more of these colors to make it less saturated. Well, what we can do is just make the curve wider like this. A very saturated color that's just purely one color, one wavelength. Now we're not talking about RGB, but in wavelength again. Would be just one sharp peak. This would be a very saturated color. There is no red in there, there is no green in there. And something white, that's a very desaturated color. This would be somewhere around here. So that's what saturation is. Saturation is the width of our curve. How much it wants to purely bounce one wavelength, or if it's willing to bounce others as well. That's saturation. And of course, the value is how much there is, if there's none or if there's a lot. So value would be moving over here And saturation would be moving from this width to this width. And then the color, it's like if we want not a desaturated yellow, but a desaturated green, we just have to move it over here. So this is the color that we get, except there's no magenta in here because we are talking about the color spectrum. Now there is a model for picking these colors that does this for us. HSV. This stands for hue, saturation, and value. A value is this one. Saturation is moving outwards. Doesn't matter if what the value is, it's just moving outwards. That's saturation. And hue is where we are in rotation on the color wheel. Now this hue, does that mean we're moving over here across this? No, it doesn't, because this was the light spectrum and we have magenta in here. It's moving across the color wheel, not the light spectrum. For a huge part, it's the same. For this entire part, that'll be the same. But hue is where we are here in our color circle. And that's not the same as the visible light spectrum, as explained earlier. So hue, we are moving around here, just like here, it's visualized in a pyramid here, where saturation is how much we move outwards, and value is how much we move this slider. Color, what is color in terms of your digital software? Red, green, and blue. We can select how much red, how much green, how much blue we want in there. Also HSV, hue, saturation, and value. If I move the saturation up a lot, then this will move it outwards, and this hue, it will move it across the circle, it will rotate, and value, that's just going to change this slider. This very large number has now become 255. 255 is 1 byte of number, so our red, green, and blue, it goes up to 255. But we could also express it in terms of a value between 0 and 1. 0 being nothing and 1 being full. Let's express color in terms of red, green, and blue. So we have a slider here, and this is nothing, and this would be full. So this would be 0 and 1. And this would be 0.5 over here. No red light, no green light, and no blue light. What do you think that is? Well, let's look at this black here on a color picker. Wow, it's 0111 apparently, so it's not perfectly black actually. No red, green, and blue, that's black. What if we do full red? And I'll put this in the next layer. Full red, full green, and full blue. Well, let's again add red, green, and blue. We get white. So red 1, green 1, and blue 1 is white. Red 0, green 0, and blue 0 is black. What if we do each one at half? Half red, half green, and half blue. What is that? Well, they are all the same value. So there's an equal amount of red, green, and blue light. So what's in between red, green, and blue? Well, in the middle we will have white. It's an equal value of red, green, and blue. But then we're not full. We're not at 255. We're at half of that. So half of all of these would be gray. What if we now remove the blue light? We have some half. We have some red and some green. No blue, so we will have some yellow. What if I have some red, and over here I'm going to add something to it? I'm going to draw this again, but in a smaller scale. I have red light, and I'm going to add a green light to it. This one has 0 as red and 0 for blue and 1 for green. Well, if I add these, I'll have to add this value to this value, this value to this value, and this value to this value. This is a half plus 0, so that's still that's a half. So this is the answer. Half red, 0.5 plus 0 is 0.5. 0 plus 1 is 1. So by adding green light to some red light, we have some red light and a lot of green light. So a lot of green light and some red light, but not full. Let's try that. I'm going to add a lot of green light and then some red light. And apparently that's this color. It is perfectly at the top. This is lime, I believe. So we've added 1 portion green, half a portion red. We have come over here. If you added full green and full red, we would have had full yellow. But now we are only adding half red, so we are on here at the top. That's how addition works here. And addition with half red and half red, that would be full red. We are just adding these individually. Subtracting, I could subtract half red from half red and I will get nothing. So that's the subtractive blend mode. And if I have red, green and blue light and I want to make that into cyan light, I have to subtract red. So if I pick red, green and blue light and I subtract red light, I will get cyan light. Because I get these, I get this, I get this. These together, what's in between them? Cyan. And again, we can demonstrate this. I'm going to pick some red, green and blue, but not that saturated. So that's just gray here. I want to make this gray light into cyan light. Now I need to subtract. I will subtract some red again, and it's at half strength. I should get cyan light. Yeah, and it's dark cyan because they are not full. So this is how you can think about the color blending. This is the blend mode as just a kind of operator. Over here I have a lot of red light, let's say 0.9. It's not all there. It's a value of 0.9 red. And some green, let's say only 0.4. So we have light, which is 90% red and 40% green, and there's just no blue in there. And we are going to multiply this. What happens if we multiply by white? White is full red, full green and full blue. So we are going to multiply everything by 1. Nothing should happen. What if we multiply it with black? We have no red, no green and no blue. 0, 0, 0. We multiply everything by 0, it will be 0. So multiplying anything by black will just make it black. Multiplying by white will do nothing. What if we multiply it by full red and no green? Then we will keep the red value and the 0.4 will multiply by 0 and it will be nothing. So multiplying a lot of red and some green by red, it will make it red because the green, it will die off. And now, what if we multiply it by itself? What happens if we multiply 0.9 by 0.9? Well, that's 90% of 0.9. So that's still a lot. 90% of 0.9 will be the answer. but the green 0.4 multiplied by 0.4 will only be 40% of the green. So the red large value, it gets to keep most of it, while the green value, which is small, it has been more than halved. So we are darkening it because it's always being multiplied by values smaller than 1. But something else is happening. The large values are dying off slower than these are dying off. So what this means is that it got more saturated. Because this red color, it will be very red. And green, how green it is, that will die quickly. Let's multiply a color by itself right now. I'm going to pick a pinkish red, and it's a bit dark already, a little bit. Let's multiply by itself. I'm color picking this color. Now, what will we see if we drag the color picker across this? It will darken, right? It is obviously darkening. Correct, this one is moving down, but something else is happening. Let's look at the saturation. By multiplying a color by itself, we have darkened it and increased saturation. So these are all the arithmetic blending modes. All our blend modes, they still follow this logic of manipulating red, green and blue values. All of these, how they work, what they do, you can understand them by looking up what they do and thinking about what that would do with RGB values. You may have heard that to draw your shadows, you shouldn't, I will draw it over here, you shouldn't shade with black, right? Shading with black, it doesn't look great. If you want to draw a sphere. In shadows, it gets darker, of course. I want this one to be normal and this one to be... In shadows, it gets darker, of course. But shadows also actually get more saturated, typically. If you want to draw a good shadow, you need to draw it not only darker, lower value, but higher saturation. That will give a more natural shadow. To darken and to increase saturation, what have we just learned? We can do that with multiplication. So to draw, in order to draw this shadow, if we want it to darken and increase in saturation at the same time, we can use a multiplied blend mode. What if we want to draw the highlight? Well, that would be if we want to go this way, that would be the opposite of multiplication, so that is division. If we divide this color by itself, it should become lighter, brighter and less saturated and eventually reach white. If I move with my color picker over here, we can see that it gets darker and more saturated. Now, in reality, it's not as simple as multiplication, but multiplication is an effect that darkens and increases saturation. So we have these simple arithmetic blend modes that you can predict what they do by thinking about the RGB. We have blend modes that try to mimic how light works in real life. And we have just pretty much blend modes for artistic purposes. Here I have made some renders, and this is a drawing I made just an hour before. And this is to explain, try to explain something about this a shadow becoming darker, of course, lower value, but also more saturated in shadow. Here I've made a sphere which actually keeps the same saturation everywhere. But this doesn't look realistic. Look at how red this highlight is. This is a very strong highlight, but this is a bit more accurate. One reason that shadows are typically more saturated than highlights is because of this specular reflection. If we are looking at the shadow here, everything's the same. However, this is also already a purely saturated circle. But in here, a reason that our shadow is more saturated is simply because our highlight is less saturated, because it has this white highlight over here. But this highlight, it has desaturated our entire light. Our shadow kind of keeps our saturation, but a specular highlight is a big reason that shadows are more saturated. And here only the value is changing. Yeah, maybe I should just demonstrate this right now. 3D software time. Here we have a sphere. And in order to demonstrate this, I had to change the color management. And what we are seeing here, we can now put the specularity back. This is the specularity. I can also put it a very high number, like 5. You can see this has made our object more white because our light is white. But if I remove the specularity and roughness too, and then I pick my color picker here, I look at the saturation because that is, we want to see in here whether or not our shadow is changing saturation. Turning the specularity off, we actually get a color that has the same saturation everywhere. We can look at this S value, 0.297, 0.319. It is hovering around 3, but if I enable the specularity, the white here is of course desaturated. Saturation 0. And if I move here, saturation is still very low. In a specular highlight, it can reflect that light. We are blending with white. What happens if we blend this color that it is with white? We move more to here, we get less saturated. Now something about rendering, if I look at this shadow, if I move around it, this shadow does not change. I'm just looking at this from different perspectives. If I put the specularity on, the specularity is now here. The specularity, you can see it moves with us. These scenes, they are very simple. In real life, we might not have a perfectly white light. We may not have this is just a black environment. This scene is simplified, and you shouldn't use this to paint because it's not a good model of reality. We have colored lights, we have colored shadows, but you can use this to draw. So this sphere, I'll now draw another sphere. I'll do blue this time. We can use the theory that we've learned to try to shade a sphere and then add some other things. Now I can use luminosity to make a shadow. Oh, I want to have this one. And I can make it brighter over here. and then even darker here in shadow. So with just a few brush strokes and luminosity, we have already something that, yeah, that looks like a shaded sphere, right? And we can look at the color picker. What luminosity has done, it has changed the saturation too. And in here, the saturation does not change, but this is because of our specularity, for example. There may be many other factors too. And in real life, our shadows are colored, our lights are colored. But in a simplified model, this is something like how we should shade our sphere. So we can use luminosity to make this part even darker. And I would like there to be a ambient occlusion effect all the way at the bottom. It's weird because there's no floor, but that doesn't matter that much. And let's make it even brighter. Let's make that to make it fully white. I can't use this color, and the color for luminosity doesn't matter. I can draw with orange. It's only the value. Luminosity is going to change this color into what value it should be. So I can only draw with luminosity now. If I put it at a half and I draw over here, it will be one perfect color. The saturation did change. It changes all over the place, but luminosity will change that saturation from this color back into this color. So luminosity, as a layer, for example, it is non-destructive. But if you want a perfect white, you have to pick white over here, and then I can make a very sharp highlight like this. And maybe I want some more reflected light over here. Now we have used only luminosity to draw a sphere, and luminosity, it does the saturation and value, it does that for us. And we can go back anytime. I can say, well, actually the shadow, I want it to be brighter. I can do that. And this might actually be a cool effect because of, for example, bounce light, which was discussed in the last lesson. So maybe I can make this part a little bit brighter in our shadow, because maybe there's a floor over here. And I'm going to smooth and blend it a little bit. And over here you can see, not a fan of luminosity. Well, it is a brush that does everything for you, and if you want more realism, luminosity has not given our light any color, it has not given our shadow any color. Luminosity draws how it would be seen in white light. So the perfect thing would of course be to pick your unique color for each and every brush stroke, because reality is more complex. There are colored shadows and there are colored lights. Luminosity and this light, it works with white light. Our highlight here, it's white too, and our highlight here is white, because the light here is white. It could be another color. We have acted as if light was just a mix of red, green and blue light, but that is how our eyes work, that is how our screens work. Actual light, it doesn't care about red, green and blue, it's just a mix of everything. Now we might see it, oh yeah, there's some green in there, there's some blue in there, so that must be cyan. How light actually works doesn't care about that. Let's look at this example. This yellow cube. In here, our yellow cube was red because yellow could reflect red and green light. So our yellow cube here, it was a mix of red and green. So the red wavelength and the green wavelength, because we have simplified it using RGB. What if it was the actual yellow wavelength? It wasn't a mix of red and green, because our yellow here, we saw that it can reflect red and it can reflect green. So it's obviously red here, right? So it can reflect red. And in order to make it yellow, it also needs to reflect green. So this was yellow and green. What if this yellow cube was actual yellow wavelength yellow? It wasn't a mix of red and green yellow, because that's the way our eyes see it. It was the actual wavelength yellow. The wavelength yellow does not bounce red. So if you look at this picture, you look at white light and our limited human eyes, you look at this, could you tell whether the yellow cube would become black or red in red light? You actually can't, because you don't know if this cube is yellow because it reflects yellow, or if it reflects red and green, which you recognize as the average of yellow. You don't know. This yellow cube, it could have become dark black. That's possible. If this yellow cube was a yellow wavelength cube that does not want to bounce red, it would have been black. But apparently it bounces red, so it must be a mix of red and green, and maybe even this entire part, because of, you know, the saturation. But this appears as a decently saturated yellow cube, so maybe it was red and green. Over here it bounces red, so it must bounce red. What if it was the actual yellow wavelength? Then it would be black. Our eyes only see red, green and blue, and that's enough to understand these colors. We can see yellow, although we don't see the wavelength yellow, we just see red and green at the same time, or we recognize those. And in the yellow wavelength we recognize red and green light. But our eyes cannot tell if this is yellow or if it's red and green. This is a limitation of the RGB simplification that we have worked with here. RGB is great because that's how our eyes work. But if we are going to have steps in between of light bouncing, we don't know how that light bounces, because we can't see whether that light is yellow light or red and green light. How to solve this? There's such a thing as spectral rendering. Now, these are some images from a thread of Blender. Blender here. It works with RGB. That's great, because you don't have to keep the entire spectrum in mind. You can just pick 3 of these. The simplification of RGB is fantastic for our software because it's simpler. It has to deal with less numbers. It's actually not correct in some edge cases. Here is RGB rendering method compared with a spectral rendering method. The spectral rendering method doesn't just bounce red, green and blue, but it bounces a whole lot of them, a whole lot of frequencies. So this is spectral. It's just a lot of these in-between colors. In some edge cases like this, it gets different results. And the material, which is a range, much more complex than just how much red, how much green, how much blue. Our RGB renderer doesn't know how that will reflect. Spectral renderer can be more complex, and in these examples it yields different results. And over here, and keep in mind this is a very extreme case, spectral looks a lot better than RGB, but it's just that much more complex. But this is so you can be aware that this yellow cube, in RGB it will become red, but in the real world it may also become black. So do use the RGB simplification, do use RGB math to understand why things are the way they are, but be aware that RGB is a simplification of the color spectrum.